Hello everybody, welcome back to the Shumbafoot Creative Space Physics Edition, where we shall be looking at oscillations. I think we all know what oscillations refers to, but we'll get deeper into that as we go through this video. So our title for this video will be Understanding Oscillations, then a colon, the simple pendulum. That's the subtitle, the simple pendulum. So we're expecting that this will be a series on understanding oscillations, so that we get an idea of what these things are and how they affect our daily lives, and also where they are applicable in our daily lives. So let's get on with the video. We shall start by looking at some definitions and explanations so that we don't lose each other during the course of the video. But we're going to define 4 key words in this video that are going to help us understand this thing called the simple pendulum. Okay, we're going to start by looking at oscillation of an object, and I think we're very familiar with objects. What an object is, I don't need to explain that. So we also have oscillation of waves, electromagnetic waves. We also have such, but we're going to be looking at an object, particularly as a point mass. If you actually look at the idea or the phenomenon of the simple pendulum, it deals with stuff which is quite small, but in our case we're going to be dealing with the pendulum bob, as you're going to see later on. But we use it in place of a point mass because it's impractical to deal with a point mass. It needs other sophisticated or complex machines or conditions which are not very practical in most of our cases. So we are going to define the oscillation, which is the regular motion of an object at a fixed point moving back and forth passing by the point. So it starts at rest vertically, as you're going to see later on with the example that we're going to look at. It starts vertically in a vertical position. It's stationary, suspended, the pendulum. I'm talking about the pendulum. And when the pendulum is displaced or pulled at one side, it's supposed to come back to where it was at first when it was at rest, stationary, and then it passes by that point and goes to the other side, opposite to the side where it was pulled. That's what oscillate, and it has to return back to the point of the initial point, the point of rest, which that the coming back of that pendulum to that point is referred to as the restoration. We also have what you call the restoring force, which is the force that enables the pendulum to come back to that initial point of rest. Or we can even look at a spring, for example, something that's connected to a coiled spring. If you pull the spring downwards, it will come back up with the force, but it will pass by the point where it was stationary, and the coil will be squashed. But it won't be squashed for a long time. It will expand again, and it will come back down. That pendulum will come back down, or whatever weight, let's call it the weight, to come back down and pass by the point of rest, and extends way more, so that it goes to the maximum point of the stretch, which the weight can stretch the coiled spring, and then it does that until the dissipation overpowers the motion, and then we find the weight coming back to rest. So that needs to be done. So we need to also look at the elasticity of the spring. In this case, we're going to be dealing with a string. That string needs to be light and inelastic so that we don't have problems in the swinging. We need the swinging to be smooth. I hope you're getting what I'm talking about. I've already defined some of the terms here, but let's just go through and read all of them. Okay, so a pendulum is a weight suspended from a fixed point, enabling it to swing freely. So we're just basically saying the fixed point is where the pendulum is in line with the vertical line that we'll look at later on, which is called the normal. It's an imaginary line, but we're basically saying it's in the vertical axis. It's stationary there. It's not pulled. It's not yet pulled. So we're expecting it to then be pulled and then it starts swinging freely. But for us to have a perfect free swing, we need to ensure that the string itself or the rod are in good condition, or in the desired condition, inelastic and light. So then we look at period, which is the time taken for the pendulum to complete a swing from the initial position of displacement with the maximum potential energy and back to that position. The initial position of displacement is where we know what Okay, let's go to displacement, then I'll explain what I want to explain. Displacement is the movement from the initial position to another. So when the pendulum is moving from that vertical place where it is the place of rest, we then move it at an angle, preferably less than 5 degrees, that angle, because of this idea of simple harmonic motion, which is defined as the motion of a particle about a fixed point, like what we saw with the pendulum. It's at a fixed point, or at that fixed point where it's stationary, such that when it is pulled, its acceleration is proportional to its displacement. So the acceleration from the point where it is pulled at and coming back to the original point, that path in which it moves, that arc that it moves in, is what we then call the angular displacement, and it moves in that arc. The displacement and the acceleration in which it moves at is proportional to that displacement from the fixed point, and is directed towards the point. So that's what I was explaining, from the fixed point at rest and then to the point of displacement, that path, that arc which it creates, preferably less than 5 degrees for the angle theta, which we'll look at very soon, because we will lose the proportionality if it goes if the theta increases in terms of degrees. We will look at the sine theta and stuff that we'll look at very soon, so that we get to understand how the forces work. But for more explanations on these forces, I would recommend that you first watch the force and motion video, or you can watch it afterwards, so that you don't have to deal with a lot. But it's good that after this video you go and watch that force and motion. It's also on the YouTube channel, Shumbafoot Creative Space YouTube channel. So you can go and watch the force and motion video under the physics playlist, and then you get to understand, or it should be under the mathematics playlist. Yes, you get to understand these forces. It's under mechanics. Okay, so without further ado, let us get into the core business of this video. I hope you have understood these definitions and explanations, so that you don't get lost as we move on to the preface of the video. Okay, so now we're going to look at a brief summary of what we're going to be looking at. I'm not going to read everything, so just go through everything on your own. It's not a lot, but it's important for you to take note of. I'm just going to highlight a bit of what we need to know. So first of all, we have what we call the normal. You shall see a broken yellow line, which is vertical, in line with what we call the retard stand. You shall see the retard stand is those gray lines you see, the vertical gray line on the diagram on your left. That's the vertical rod of the retard stand. It can be a rod, it can be just a block of wood that's vertical, just to give the height which we need when we are doing this experiment, so that we have space for us to measure the different lengths for our experiment, as you're going to see later on. So, and then we have the clamp, which holds that blue line, that blue vertical line. That's the string that holds the pendulum bob, which is in the design of the earth in our case. It can be made of different material. As you can see, we have to have the same size, shape, weight and material for this experiment. But if you want to compare the effects on period for the different pendulum bobs with different material, like let's say one is made of molten clay, the other one is marble, the other one is glass, maybe the other one is metal. You see, the other one maybe can be rubber, but they have to have different material, so that you can see the weight of the material, the density and the volume and whatever. You can use different kinds of variables with those pendulum bobs, like the ones highlighted here. We can have different length, like in our case we can have varying angles of displacement. Like I said, we need to use 5 degrees and below for simple harmonic motion. But if you want to do more, that's whatever you want to do, you can also do it. And also maybe different material of the pendulum, like I highlighted, different sizes of the pendulum. You can also look at that, and many more that you can look at, etc. And to see how these different factors affect each other, or affect the period of the oscillation rather. So that's basically the aim of the experiment. We are trying to see the effect of these things on the period of oscillation. So does it take a long time for the pendulum bob to swing from one point to the other point, or it takes a shorter time to move from point A to point B in terms of the angular displacement? That's what we're trying to look at. Maybe we can then find the rate of oscillation and all those things, the kinetic energy and the potential energy that was involved, and how it changes because of the forces acting on the pendulum bob, because you see that it will start very fast, but it ends up, the speed ends up decreasing gradually as it comes to rest to the initial point where it was vertical and in line with the normal. So what we are going to do next, we're going to look at the precautions, and then from there we are going to then try and analyze this diagram that we're seeing on the left. So the precautions that we have, we only have 3 there, but you can add more. It's just that these ones could fit there, so if you can add more, that would be great. Even if you can put them in the comment section on the YouTube channel, that would be great. The first one is perform this experiment where there is no wind or any form of air resistance. I think that's self-explanatory. You can just see, even with the material that we're using for the string, it's very light, and also the string should be inelastic, but the wind can disturb the movement, the swinging of the pendulum, because the pendulum has to freely swing from one point to another, and it should not wobble as it moves. And then the second point is, if you're using a string to hold the pendulum, like I said, it has to be inelastic, and it should be straight even as you're pulling. The way you pull as well determines how it is going to move. So you have to be steady as you're pulling. Don't make your hands move as you are now releasing the pendulum. Make sure you are steady as you're releasing the pendulum, so that the string does not wobble as the pendulum is oscillating. Then this example is a lab experiment, so we're going to be using some lab apparatus on benches, work benches, so that we avoid any injuries. We're not going to do them on we need wider surfaces, so that's why we have the third point there, which is more of a safety precaution. You just have to avoid that pendulum experiment to hurt you. It's not really dangerous. It's not a dangerous experiment like when you're dealing with chemicals, with fire, with whatever. Those things can damage you, can hurt you. But this experiment, you can even give a toddler and they can do it. It's a very simple and safe experiment. So to avoid any problems, just make sure that your apparatus are stable, so that it does not fall on you or on your feet. You might move away, but maybe your feet might get injured as it falls down, because of the height from the top of the bench to the ground. That's a very big height, a very great height, which can cause the retard stand to accelerate as it moves down, and yeah, the impact with your toes and your feet will be very painful, very painful impact. So make sure you don't put yourself in such a dangerous situation. But anyways, let's move on and look at the parts of this retard stand, and also the pendulum itself, and whatever is involved in this experiment. So I think as you can see, the diagram should be very clear. We have a side view there, the left, and then at the right we have the front view, how you see it as you're looking at it from the front. We have the clamp, which is right at the top there. You can unscrew or screw it so that you can tighten it to hold the string. Remember, we don't want the string to disturb our movement, so we have to make sure that it's tightly held by the clamp. And also the string itself should be inelastic, and the rod should also be proper. It should not it should have uniform weight from the one end to the other. We don't want rods that are weird looking and have lumps or whatever defects, so we need to avoid that and make sure that our experiment is very, because things can happen. It can even cause greater air resistance as the pendulum is moving, that can cause air resistance. So we need to make sure that it's smooth and it should look like a rod. We should not see something else on the rod. And they have to be very light in weight, both the string and the rod, because you're going to see later on this experiment involves the effect of gravity on the pendulum. That's the force of gravity also is an effect on the movement of this pendulum bob. It also affects the restoration force, which is the force that a component of that gravity. You're going to see it in the next slide. So we have the pendulum bob, which is connected to that light inelastic string in our case, and ours is just looking like the planet Earth, but it's not the planet Earth. Don't think this experiment is for the planet Earth. No, it's just something to make the video interesting. But make sure that it's of a finite mass. Remember, we need some constant variables and then the other variables that are changing. In this case, the variables that are changing are those of the length of the string, because that's what we're trying to look at, or with its effect on the period. The rest of the variables, like the mass and the material of the pendulum bob, they have to be constant. They have to be the same. You cannot vary them, because if you vary them, they will also contribute to the effect on the period, and you won't be able to see the true impact of the change in length on the period of oscillation of this particular pendulum bob. So make sure that is in place and you have understood that. And then we have our rhetoric stand, which is holding everything. It's giving that height for our pendulum to be suspended, for it to be possible. So that's the apparatus that we use, the rhetoric stand. And then it has a base, which is usually heavy, but is connected to the vertical rod there, which helps to balance everything. As you can see, it's wide. The base is wide, so that it gives a balance for everything not to fall over. So that's it on the front view that we're seeing, and it's basically the same thing with the side view, so that you can see how it looks like. But we have the theta there, the angle of displacement of the pendulum. So the arc that is created as you move from the vertical position of the string to where it is now, where it's inclined, that movement of the arc, which is represented by that yellow line, that is what we call the angular displacement. But for our case, we are looking at the angular displacement of the pendulum bob. So it's not that yellow line. We have to move it close to the pendulum bob, which means it will be a bit longer. The arc will be a bit longer, so that will give us the angular displacement. And then if you look at the side view, we have that triangle there with a right angle shape there, which we use. It's called the set square. Yeah, it's called a set square, but it's actually in the form of a triangle, or it can be in the form of two rods, or two rods that are perpendicular to each other. Yes, so that you form that right angle. That's what we use to ensure that the string is in a vertical position, to make sure that it's directly vertical and it's directly in line with the normal, our imaginary line, remember? So that's the normal, or directly in line with the rhetoric stand. Yes. So that's what we call 90 degrees. As you can see, it's written on that side note there, highlighted in black. So just read that. That's basically what I've explained. And then we have our length L of the thread or the string. Remember, it's supposed to be light in weight, so I'll just call it a thread, but it's supposed to be a light inelastic string. So that thread might be a bit problematic if you're using greater masses. It might actually not be strong enough to hold those masses. So if it's a light inelastic string, it will be better with a very smaller diameter, but still it has to be light and inelastic as a string, so that it does not have an effect on the weight of the pendulum itself. Okay, so now we're going to look at the forces involved in this experiment. But before we look at the forces, let's look at that instrument that's there at the top, which is in the form of a semicircle. That's what we call the protractor. It gives us we use it to measure the angle of displacement. So that's what you use to determine the angle. We don't guess. So like it's written, a protractor used to measure the angle of displacement. So just research on that protractor and get to know more about it, but it should be a very common tool or instrument. Okay, so the forces that we have what we call the tension T, which is the force that the string that's in the string when it tries to pull the pendulum, and the pendulum also pulling the string in the opposite direction. So that's what we're trying to determine here, and we find that using the gravity, the force of gravity, which we know we can find that using Newton's second law of motion, which talks about the relationship between the force and the acceleration, that for a constant mass the force will be directly proportional to its acceleration. You can research more about that Newton's second law of motion, or you can even watch the videos of the In the Planet series or the Dwarf Planet series, or the podcasts. They're now podcasts, by the way, so go and check them out and find out more about this. But if you really want it quick, if you want to know it quick, you need to visit the force and motion video. Forces and motion video. It's on the YouTube channel, so go and find out. So that's the tension, and then the component of force which is opposite the tension, which is mg cos theta. If you know your trigonometry very well, you should know what the cos is, cosine, sine, and the tangent. You should know those trigonometry identities. We call them identities. So for the mg cos theta, it's in line with the tension, as you can see. How we determine those, you need to watch that force and motion again. Everything is explained there, even how we find the resultant force that will cause the pendulum not to move, or rather not to rupture the string. That is explained in that video, how we determine that using the Cartesian plane, yes, or what we know as the x and y axis. Yes, so just get to familiarize yourself with that in that video. So we then move on to the mg sine theta, which you're seeing there in orange, which is the component of the force normal to the plane with the tension. These two forces, the two components, they are components of the force of gravity that's pointing downwards, which is the force that we know pulls you to the ground. In this case, we are not going to be dealing with the gravity on Earth. I need to stress that point before we look at the example we're looking at. We're not going to be using the gravity on Earth. We are going to use a hypothetical gravity that we're going to find out very soon, which is less than the one on Earth. But you can use the one on Earth, which is 9.81 meters per second squared. The one we're going to use is around 7.9 meters per second squared. So just get to understand that, so that you get yourself used to using different types of gravities, because each and every planet, each and every asteroid, each and every star, each and every whatever object is in space, including Earth itself, they have different values for their own gravities. Yes, so you need to get used to that. So we're going to see that the mg sine theta is what I refer to as the restoring force, which is the force that takes that pendulum bob back to its equilibrium position, where it was vertical, in line with that normal line that you're seeing, which is that broken yellow line that I was talking about, which is in line with the retard stand, vertical. So from where it is right now back to that line, that is what we call, the force that takes it back there is what we refer to it as the restoring force, and that will be equal to mg sine theta. So those are the three forces that we look at in terms of gravity, that have a relationship with gravity, and then we also have that tension, which is also due to us having that string, the tension in the string, because we have two things on either side of the string pulling the string. We have the retard stand, which is ensuring that the string or that the pendulum does not pull the string and fall to the bench, on the bench, and also we have the pendulum, which is trying to pull the string away because of the gravity that's acting upon it. So that's why we have that tension. And then if you see on the side view, we have mg there, which is basically telling you that it's the force of gravity acts vertically downwards. That's why you see on the other diagram, on the front view, it's vertically downwards, and the other components are at right angles to each other, but they are positioned in such a way that if you take those three forces and create a coplanar diagram, if you talk of coplanar forces, you I'll start delving into the other video which I referred to you. So make sure you visit that video and get to understand more about these coplanar forces, so that you don't get confused when I'm now saying this terminology of mine, this mathematical term, coplanar. So get yourself used to that. If you take those three forces, like I was saying, if you arrange them in a sort of like a vector diagram, you'll find that the force of gravity will be like a resultant force that acts upon this pendulum bob, and then these other two are components of that force that lead up to us having a force of gravity which is prevalent. But in this case, we see that the pendulum is not moving, so it will suggest that the tension is stronger or is greater than the force of gravity. That's why the pendulum is not able to pull the string away from the clamp, or to even tear the string or rupture the string, whichever term we can use to describe it being torn apart. So that's it for this segment, or for this part. Okay, so before we look at something else, let me explain something. So let's assume the pendulum is now at rest. It's back to that vertical position in line with the normal. What you realize is the mg will remain vertically downwards, but the mg cos theta, as it moves, it will eventually become vertical and in line with the mg, which is the force. Remember, F is equal to ma. That's the one I was referring to as the Newton's second law of motion. That's why we have mg. The g is equal to the a, the acceleration due to gravity. A is acceleration. In this case, we look at acceleration of free fall. Yes. So we're going to, because free fall means that we're only dealing with gravity. That's the only force that is making this pendulum fall. No other forces are involved in this experiment. That's what all other forces are negligible. It's just the force of gravity that is prevailing over this pendulum bob and causing it to move downwards. So the mg cos theta will be equal to what? To the mg, and that's because mg cos our theta, it means it will be it should be equal to 0. Yes, because the y-axis vertically is equal to 0. The x-axis also is equal to 0. We're going to see that with the sine theta, something will happen. Cos theta, if theta is 0, then cos 0 will be equal to 1. So mg multiplied by 1 will become mg. So that's why when cos theta comes vertically downwards, or if it points vertically downwards together with mg, it will still be equal to mg. So no violation of mathematics there, or mechanics there. And then the mg sine theta will become horizontally, pointing horizontally to the left side, towards that side view diagram. So that means that our theta will also be equal to 0 in the x-axis. The sine theta will be equal to 0 in the x-axis. So mg sine 0 will be equal to, sine 0 will be equal to 0. And we know mg multiplied by 0, anything multiplied by 0 is equal to 0. So which means there won't be any component, it will be equal to 0. There won't be any component of the gravity in the horizontal axis. And that's why we then say when it's at rest, only the force of gravity is in effect there. And also we have the tension as well, but the tension is equal to what? Is equal to mg. So that's why the pendulum will be at equilibrium. We call that at equilibrium. It's because the tension will be equal to gravity at that point. And then in terms of energy, let us also look at energy. So with energy, we have the kinetic energy, which is the energy of the pendulum in motion, when it's in motion. And then we have the potential energy, which is the energy that it stores as it is about to leave the point at which it is at. For example, at the point where it is right now, as you can see it, it's a bit further away from the normal at that angular displacement theta. So we are expecting that from that point is going to fall back down and come back to that normal line, or that vertical line, with that vertical broken line. That's where we're expecting it to be, and it will pass by there and swing to the other side. That's what we're expecting. So in terms of energy, how we explain the motion, where it is right now, it has maximum potential energy. It's not going to go any further from there, as you shall see later on. It's not going to go any further from that position. It's going to come back towards the normal. And as it is in motion towards the normal, kinetic energy will be increasing as it comes to the normal line. And potential energy will be decreasing up to 0 at the normal line. So at the normal line, kinetic energy is at its maximum, and the potential energy will be at 0, because there's no potential of movement from there. The potential will start increasing as it goes towards the left side now, as it swings to the other side. So when the restoration is happening, the potential energy is decreasing and kinetic energy is increasing. Then as it moves from the normal to the other side, the kinetic energy starts decreasing, because the restoration force is now in its negative. It's now negative kinetic energy. So it's now decreasing. The speed, the acceleration will start decreasing as well as it is moving on the other side. And what is now being gained is the potential energy. We'll look at this in future, hopefully in the near future, but probably not in the near future. There's a lot to cover in the planet series that I'm looking at, so just be in touch, stay tuned, and find out more about this energy stuff as we look at other examples in future. But that's basically the idea behind the potential energy and the kinetic energy. So as it is moving to the other side, the potential energy increases until it reaches its maximum, and it will be maximum potential energy and some negative kinetic energy. Okay, now we're going to count the number of oscillations for this small distance, this short distance, L, or the length of the string, which is short, L in this case, and then we're going to look for the time as well for the longer distance in the other example. So let us count for this one first, and then we'll go to the longer distance. So wait for it to start from the right. You don't start immediately as you pull, after pulling the pendulum or after releasing the pendulum. So you wait until you're confident that you can catch up with the oscillations. So we'll start from the left side. Let's start from the left side, our left side, as you're looking at the pendulum. So make sure your stopwatch is ready, so that when you count your 20 oscillations, your stopwatch will also be running the time. So ready when you are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I think we are done with this counting of hours. We can see our time is 11 seconds, 11.94 seconds. That's the time that I've recorded. So let us see how we'll do with the next one. Okay, so reset your stopwatches. It's now in motion. Ready when you are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now our time will be 41.33 seconds. That's the time for this longer length, with the string having the longest length. It's around 41.33 seconds. That's what I found. Maybe you can share what you have found on your side. So that's basically how we carry out the experiment. So you pull the pendulum, you release, and then it oscillates. So let us then see the table of results for the experiment that we are looking at. Okay, so I've prepared this table of results which we're going to use to analyze the relationship between the length of the string and the period of the oscillations. So we have seen that the second column is what we're doing. We're basically counting 20 oscillations, and then the time that we got will be in seconds from our stopwatch. Yes, and then you record the time there. That's what I've done. And then we have the length of the different lengths of the string that we used and the corresponding time for 20 oscillations. And then you divide these times by 20 because we're using 20 oscillations. So the period that we are looking at of each oscillation is basically the period of a single oscillation. So you divide by 20 to get the corresponding period t for each oscillation. How long did each oscillation take? Yes, it should be the same, so that's why we divide by 20. And then we are assuming that in those 20 oscillations, the way it was swinging was the same. It was not getting tired. Let me put it that way. It wasn't getting tired. So it had the same energy as it was moving. And then the t squared, we'll find it just now. There's an equation that makes us use t squared, which is called the equation of a straight line. We're trying to make it easier for us to analyze the relationship, the proportionality between the two variables, the length and the period. So we have to rearrange a certain equation so that we can find so that we can get a straight line for it to be easier to analyze. And that is what we call the equation of a straight line, which is y is equals to mx plus c. We will look at it later. So the y will be the t squared. That's why we have t squared there. So what we do is basically we take 2.24, then we say 2.24 squared, and then we get 5.0, 2.00 squared, 4.0. And I'm putting it to one decimal place for a reason. You will find that in the equation there's a value. It should be the length that we'll put in one decimal place. That's why that one will also be in 1 decimal place. And then also the units are in the header there, the headings row. We have the length in meters, the oscillations in seconds, then the period in seconds, the time for oscillation in seconds, then the period in seconds, and then our t squared will be in seconds squared. So it's 5.0 seconds squared, 4.0 seconds squared. I think you know why. If you see on the gravity, force of gravity, acceleration due to gravity rather, the unit is in seconds squared. It's meters per second squared. So that's seconds squared. That's where it also comes from. And then take note that the angle of displacement is the same, theta, and we are saying that it should be less than 5 degrees because we want it to be a simple harmonic motion. That's what we're aiming for. And then also our acceleration due to gravity will be 7.90 meters per second squared, like I was saying. So we'll calculate it later, but for now let's just look at these values, get to create your own table and do your own experiment and see if you can get your values. They are not supposed to be like mine, so I intentionally used a different acceleration due to gravity or due to free fall, because we're looking at free fall here, where gravity is the only force that we are dealing with. Okay, so before we draw our graph, let us look at this. So we're going to be looking at the period of oscillation, just trying to understand it. So the period of oscillation, like I said, is the time of 20 seconds divided by the time for 20 oscillations, divided by 20 oscillations. So because the period t is the time for a single oscillation, like I said, so we then divide the value for 20 oscillations with 20, so that we get for one oscillation. In this case, if we have 21.0 seconds is the time for 20 oscillations, then if we divide by 20, we then get 1.05 seconds, which is the time for a single oscillation. And then our t squared will basically be 1.05 squared. Then we get a 1.10 second squared. That's the t squared. So if we look at the formula that I was talking about, it's on the right. So we should know that the length of the string is directly proportional to the acceleration due to gravity, as we see in the equation that we see in yellow, highlighted by the gray. Okay, maybe not directly proportional, but it's proportional to the length. So if we see that, that's how we express it, and the 2 pi is because we're dealing with angular displacement, as I said. So that's why we see some 2 pi involved here. So the t is equal to the square root of 4 pi squared in the fraction of L over g being the acceleration due to free fall or acceleration due to gravity, and then L being the length of the string. Then we multiply with the 4 pi squared, and then we square root that to get our t. So if we want to put that equation in the form y is equal to mx plus c, which is the form for the equation for a straight line, because I want to draw a graph using that one. So in that form, we see that in our case we don't have the c, the constant, the y-intercept. That's what we don't have. So our c, when it's equal to 0, because we don't have it, it means that we just have y is equal to mx, y being the y component. So you put in the y value, and then which is the t squared, and then our m is the gradient of the line, how steep the line is or how gentle the line is. Then our x is the x component from the x-axis that we also put in, which in this case we shall see what it will be. It will be the length of the thread or the length of the string, the way you want to put it. Remember, it will be light and inelastic. Yes, so that's basically it. So which means our equation in the form of y is equal to mx will be t squared is equal to which means our gradient will be 4 pi squared over g multiplied by the x, which is L, the length of the string. And then if you read that orange note there on the left, on your left side, you'll find that there is something that we call the origin, which is where the two axes meet, the y-axis and the x-axis, the horizontal and the vertical axis. They meet at a certain point, which we call the origin, which is basically 0. So because our c is equal to 0, our y-intercept will be the origin, because that's where the y will be equal to 0. So we are expecting that that's where our line, our straight line for our straight graph, it will be starting at the origin there. So it's a must, because c is equal to 0, it has to start at the origin. That's where the y is equal to 0 is found. So let us look at another way of looking at this. How do we find our t squared and all that? and the periods, and then we'll look at the graph after that. It's just a brief look at the period, more about the period and the gravity, that the effect of gravity as well, and then we'll look at the graph, and then we'll conclude the video. Okay, now we look at period and gravity, the relation between the two. So we know that the length is directly proportional to the gravity, the acceleration due to gravity, yes, which is g, and then the length of the string is L. And we know that the length is, according to what we're seeing here, the length is going to be directly proportional to t squared, which is the period squared. So what we are going to do here is we're going to first try and find out what's the value of the gravity that we're going to be using with the periods that we are seeing in our table, with the lengths that we're seeing in our table. So g will be equal to 4 pi squared multiplied by the L, which in this case will be 0.2 meters, divided by t squared. So the corresponding t squared for 0.2 meters is 1.0 seconds squared. So we then get our 7.8957 meters per second squared, which is basically 7.90 meters per second squared to 3 significant figures or 2 decimal places, just for accuracy's sake. But we should have put it at 7.9, because if we look in our working, our values are to 1 decimal place, so it should have been 7.9, but 7.90 just for accuracy, because we see even our other values for gravity, like we're going to see with Earth. For example, if we're going to find the period of Earth, that's how we find it. We use 9.81 because that's the acceleration due to gravity on Earth, and then 24.79 for the acceleration due to gravity on planet Jupiter. So those two gravities are different, so they're going to have different effects on the same pendulum, which is on maybe on either planet. Yes, so it's going to experience different periods of oscillation. So if we then look into that yellow box, we see that we have the period and that we're trying to look for. So instead of calculating the way we did, first finding one for 20 oscillations, and then you divide by 20 to get the period for a single oscillation, you can use that equation that we looked at first, which helps us to find the equation in the form y is equal to mx. So we have that t is equal to 2 pi multiplied by the length over the acceleration due to gravity. So in this case, if we are going to have it on Earth, acceleration due to gravity on Earth is 9.81, like I said. If we're going to have it on Jupiter, acceleration due to gravity is going to be 24.79. So we're going to compare the two with the one that we have used, which is 7.90 meters per second squared. So in our case, if we start with the Earth one, we get 0.90 seconds if we plug in the values. If we use the one for Jupiter, it will be 0.56 seconds. So if we compare it with the one for our example, we can just say, because we used our t squared is 1.0 seconds squared, so what we can just do to find the seconds in seconds is then say square root of 1, which is basically 1, because 1 times 1 is equal to 1, so square root of 1 is equal to 1, so it's 1 second, 1.00 seconds. So we then see that the greater the acceleration due to gravity, the less time it takes for the pendulum to oscillate. Yes, so it's because the gravity has a greater effect in pulling the pendulum down. So it's not as free as it used to be on, it won't be as free as it would be on our planet. Like what we are seeing, it's 9.81, and this one is like probably more than 2 times the acceleration to gravity on Earth, the gravity on Jupiter. And we can see that it's the period is way less than the one on Earth, and our one on Earth is even way less than the one on our hypothetical planet, which has a gravity of 7.90 meters per second squared. So you can see with the difference that the greater the acceleration due to gravity, the less time it takes for the pendulum to oscillate. So that's something that you may need to understand and look into as you are doing your experiments. If you want to find out more through experiments, that's it. But let me tell you one secret. If you're trying to find out how I found my values in the table of values, the table of results, this is the method I used. Just a little secret for you. But you can use this method to verify the values or the time that you get on your stopwatch. Yes, so when you do your counting and then you divide by 20 and then you get your time you divide it by 20, the one on your stopwatch, and then you verify using this method to find what t is using the same values, and then you see what t is, and then you see if your value is close to the one you find on in that equation. Where after using that equation, then it means you are more or less the same in the same place. But make sure you know the acceleration due to gravity that you're using. Don't make the mistake of using the wrong one. Okay, now we are at the last stage of this video, which is the one I like the most, but that's why you get to see what you were working on all this while, all these things that you're doing now coming together and being presented on a single graph. So we call this the presentation of results, the graphical presentation of results. And we're going to have a horizontal axis, which is the length of the string or thread or rod in meters, the length in meters, L. And then we have t squared, which is the period squared in seconds squared, as the vertical axis. And as you can see with the values, it's the same with what you are seeing in the table of results if you go back to the table of results. And then where you see it says 0.0 and 0.0 by the corner there, that is what we call the origin. That corner there, where those two yellow lines meet, that is what we call the origin. That's where the numbers start. So this one we call it the positive quadrant. Yes, on the Cartesian plane. We have a negative to positive, positive to negative, and a negative negative. This one is the positive because the values are increasing in the positive, the number line, like what many people refer to. Okay, now we're going to look at the points that have been plotted. We have those 5 points there. Ideally, according to scientific principles, you cannot come up with a conclusion using two trials or 2 points. You need more trials. You need to do the experiment again and again for more than 2 or 3 trials. So that's why we have 5 points there, which means we did it 5 times. That's why we have 5 values, 5 rows on our table of results, which are represented here by the 5 x's there in white, those 5 crosses in white. And then those 5 crosses, they are represented by t squared is equal to, the line that's created there is the t squared is equal to 4 pi squared over g in brackets, which is the gradient, multiplied by L, which is the x component, which we put. So for example, if we take 40 as our L, it means our t squared will be 2.0. If we take our 0.80 meters as our L, the corresponding t squared will be 4.0. That's what it means. So you're just putting the values and you calculate and you find what your t squared is. So as you can see with the points, they're all in line. And if you see, we drew our line, the orange line there, it's drawn from the origin. Remember what I said the origin is? And it extends all the way out, even past the 5th point, the 5th trial. Why? Because if we do more trials, we are expecting them to still be on that line, you see. So that's why it is important for us to put it in the form y is equal to mx. We cannot say plus c because it's passing by the origin. But yeah, we can say plus c, but we just know our c is equals to 0, which is basically the origin. If it was maybe y is equals to mx plus 1, let's say 1, it means we're supposed to start from 1.0 and extending outwards. Yes, but that's not the case. So you can see that it's now easier for us to see that t squared is directly proportional to the length of the string used. So as the length of the string increases, we expect that the squared of the period will also increase. So it's easier now to see than if we were to use maybe, what is it called, the initial equation, which had the 2 pi and the square root of L over g. It would probably come out like some of the lines come up with parabolas, and some will come with weird lines that have weird orientation. But we can see that a straight line helps us to just see the proportionality there and determine the relationship and conclude on the relationship. So our conclusion is these two are directly proportional to each other, and we can prove it through the equation. We can even prove it using this graph. So I think we have done justice. We have found what we wanted. What's the relationship between period and the length of the string? So that's how we can understand oscillations from this experiment, experiment that we have. So I hope you have enjoyed and you have learned a lot from understanding oscillations. the simple pendulum. Till we meet again. Cheers.